Hello everyone. For this video I'm going to explain transform of discontinuous functions. Discontinuous functions often arise when the method of Laplace transforms is applied to physical problems. With particular of interest is jump discontinuities. We need to find the Laplace transform of such functions and make it kind of straightforward. So we need to establish some theory behind it. And some ideas that start before to deal with this is to base it on something called you've seen in the past or even in previous math courses, a step function. And this is a unit step function, which let's call it u of t, and this u of t is defined as u of t picks up 0 when t is less than 0 and picks up, let's say, 1 when t is greater than 0. So you notice that here we have it's not defined at that 0 at t equals 0, right? So we do not specify value for u of t at t equals 0. That's one thing to notice. Which means that if there is, because we are interested, of course, in representing these functions in a shift, if there is a shift of the argument of ut, this jump also can be moved to a different location. So let's say, to abbreviate a little bit, so if you have u of t minus a, then if you've done this in the past, then it could stay as this. However, now it's t minus a less than 0, and for this second t minus a greater than 0. Or you can also represent it by still 0, 0 and 1, right? However, here is t less than a and t greater than a. So it has a jump at a, so the jump here at a, which is of course the value of t. So by multiplying, let's say, a constant. So if you have a, so let's say let m be a constant, and the height of the jump can also be modified. So if you have m times u of t minus a, then it's 0 when it is t less than a. However, here it's 1 times m, which is m, that is multiplied. Okay, t greater than a, t greater than a. So what does this mean figure-wise? It just means that let's say you have some function, let's say here discontinuous 1, discontinuous 2. Let's say here this u of t minus 2 here, and if it's multiplied by 2, then let's say here 2 of ut minus 1, and of course this is t, and this and the y-axis is the function. So two-step functions here expressed using the unit step function. One is u of t minus 2, which shifted by 2, kind of the concept you've seen in the past in algebra. And the next one is u of t minus 1. It's shifted by 1, but you have 2 times, so the height changed by 2, so this will make it a 2. All right, so that's kind of the graph. Of course, since we have a jump, then not continuous, so it's 0 on these. So let's simplify this formula. I think we need a little bit simplified formula. So we're going to introduce something that's going to apply some rectangular window, which turns the step function on and off in this rectangular representation, and it's going to be handy when we deal with these. So let's have a definition, and maybe change color here. Right. So the rectangular window function, it's this big pi and sub a comma b of t is defined by this way: pi sub a comma b of t equal u of t minus a, the shift t minus a, minus u, the shift of t minus b. It's going to be equal to this piecewise function here, t less than a, t between a and b, and t is greater than b. Okay, so this is a nice definition that's going to help. And of course, if you want to look at understanding this presentation here, it just means that you have a function up to a 0, then here is the pi sub ab of t, and of course this is going to be b, then it keeps going as 0 after that. So we can do some other examples to show if you have even a function f of t between a b, then have the window effect of it, and we'll see that in the examples. So any piecewise continuous function can be expressed in terms of window and step function. That's the main thing. So here maybe this to write to know in general, any piecewise continuous function can be expressed in terms of window and step functions. Let's give you some examples. Sometimes here the graph may not show much until we do more examples. So let's start simple as we have a piecewise function. Of course, it has jump discontinuity here, and let's say these are the rules that it's using, and let's say over these parts here, t less than 2, between 2 and 5, and between 5 and 8 and greater than 8. Okay, so here we can clearly from what we saw that now we have 0 to 2, right, when you look at the interval part. So of course we're working on the positive side, 0 to 2 and 2 to 5 and 5 to 8. So we can establish representation to this function as 3 times pi sub 0 comma 2 of t plus 1 times pi sub 2 comma 5 of t plus t times pi sub 5 comma 8 of t and plus t squared over 10 times u of t minus 8. Alright, so let's give you more details. So that's kind of done for the representation, just to show the beginning how we start with. So let's work on give you another rule, Laplace transform of, let's say you have u of t minus a. Of course it's going to be on S, and if you want to evaluate this, you just e minus a s over s. So if you have to do this, this is another rule that you can add, and there is a nice easy proof to it. But of course you're gonna say we're not gonna run into just this simple case, so I'll give you the others. The others are gonna be under this theorem, and one part of the theorem is let's explain. If you have this capital F of s is the Laplace transform of the function f on s, and it exists of course for some s greater than a or alpha, let's say alpha greater than or equal 0, positive, is some positive. Then the two rules that we'll add here is the Laplace transform of some function of t minus a times u of t minus a. Notice here t minus a is going to be equal to, and how you're going to find this in the examples, negative or exponential function of negative as here times the capital F of s. Alright, which means the inverse function for it, if you were to do the inverse of this right hand side, of course it works. It will give you, which will be on t, will give you f of t minus a times u of t minus a. But of course what will happen is in practice, we will do these examples, but in practice you may run into something that's not the same. which means let's do it in different color. For example, what if I have some function g of t, which means here you see previously t minus a, but what if you have some function g of t times u of t minus a of s? How would you deal with this? Well, luckily there is also a formula for it. It's the exponential of negative as times, it just here you will do Laplace transform of the function g but of t plus a, right, on s. And let's do an example for this one because it looks a little bit different, so let's do an example for it. Let's say you have let's determine Laplace transform of t squared times u of t minus 1. So g of t here is t squared and a is 1. So g of t plus a will be g of t plus 1, which is going to be t squared plus 2t plus 1. And of course now if you want to find the Laplace transform of g of t plus a on s, it will be Laplace transform of the t squared plus 2t plus 1 on s, which we've done previously for t squared, and so we'll have 2 over s 2 plus 1 and 2 over here s squared plus 1 over s. Alright, so now that we know for the t squared, we can employ in the formula, the last formula we did, so the Laplace transform of t squared times u of t minus 1 on s is just going to be e to the negative s times this 2 over s cubed plus 2 over s squared plus 1 over s. Even if you have a trig function, you can do the same thing. Doesn't matter. So let's say you have let's say cosine of t times u of t minus pi. So it just, that means that g of t is cosine of t, and here the a is the pi, and g of t plus a is just going to be g of t plus pi, which equals to cosine of t plus pi, which we know using the, you can do the sum formula for cosine, or if you know with the shift it's just going to be negative cosine of t. Alright, and so Laplace transform here, Laplace transform for g of t plus a on s is just going to be Laplace transform of negative cosine of t on s, which we know using the table previous work, that's s squared plus 1, and we have a negative. So looking for Laplace transform for cosine of t of t minus pi, on S is just going to be, we use the e exponential function negative pi of s times what we found, and of course the negative there. Let's do more. Let's say you have determined the inverse Laplace transform for the exponential negative 2s over s squared. So here we understand now from the work that we need to get something like exponential negative as times some capital F of s, right? So for here we're going to propose, so let's propose that this e to negative as is the ae to negative 2s that's already there. That means that the capital F of s is 1 over s squared, and that makes a 2, right? So f of t then, using the inverse Laplace transform for 1 over s squared, where on t will give me t. So the answer then on t is going to be the function on t minus 2 times u of t minus 2. Alright, so what else we can do? We can do some other examples from maybe that involves sketching. And I think I'll do them next in another video, just like the similar type of homework examples. But this gives you at least an idea. So you need to, what you need to do, I think at this point, is to refer back to these. So if I have Laplace transform f of t minus a times u of t minus a, then I have this function equal to this. So the shift needs to, or the delay needs to match, equals to e to negative as times f of s. If it's this just justifies it, that we can inverse that. But if it is not even similar, we can still do that. So that's what you need to focus on. Of course, the beginning was about just having the window, so let's go back all the way to the start. The unit function, then the multiple there for the height, then the rectangular window, which we will need to use and do some examples on. Then here, if you have only u of t minus a, you can express it by this exponential function of negative as over s. If you have something with it, then I spoke about it. Then these are some introductory examples. in which we start to understand what that notation and how to get the Laplace transform of it. And here, what if it's a trig function multiplied? We saw the same thing. And what if we need to reverse this? We know we can reverse it, so we know what we look for, and we just try to set up the components. Once we set up the components, we do the inverse function, and so now we know that A equal 2 and the capital F of S is 1 over 2, so this is kind of that. And from here we can talk about the window and other stuff, but I'll do that in another video.